Hello Math 30-1. So welcome to the unit circle, and at the end of this you're supposed to build a snowman. Please have handy your beautiful colorful special triangles that we should have built at the end of class last day. I know that we didn't quite finish the 30 and 60, but go back into your Math 20 notes if you don't have the ones or you were away and look at those beautiful triangles that we had and use that as you go. The first thing we'd like to do as we build the unit circle is realize that there's nothing new here. It's going to involve special triangles. So it's going to involve special triangles. It's going to involve the cast rule, and it's going to involve a little bit of Pythagoras theorem and angles and standard positions. So there's really nothing new. It's just a summary and a culmination of all the things we've learned. So first off, our benchmark angles. 360 degrees. I want you to go around and complete this and then come back and look at it after, all right? Don't just copy it. So, for example, 0 is the same thing as 2 pi radians. If I go to 30 is pi over 6, and 45 degrees is the same as pi over 4. 60 degrees is the same as pi over 3. I don't want you to memorize these. I want you just to know these. 90 is the same as pi over 2. How many radians is 120 degrees? Well, that's the same as 260, so that'd be 2 pi over 3. 135 would be 345, so that'd be 3 pi over 4. 5 pi over 6 is 530, so that's 150 degrees. We go over to 7. Oh, 7 pi over 6 is 730s. That's 210 degrees. 225, that's 5. No, that is 545. So that's 5 pi over 4, or 1/4 pi more than pi, right? We've got 240 degrees. That's 4 60s. That's 4 pi over 3. 270, that's 3 pi over 2. 300, that's 5 60s. That's 5 pi over 3. 7 pi over 4 is 745. So that's 315, and last but not least, 330 degrees is 11/30s, 11 pi over 6, or one might think of it as pi over 6 less than 2 pi, right? However you do it, those are our benchmark special angles, and they relate in terms of our special angles to those special triangles that we built last day, right? The equilateral triangle and so on. So if you can draw those triangles and you are good with radians, you're done. You don't even need to do unit circle because it's really just putting all those things together, okay? So what is the unit circle? Well, first off, the unit circle has a radius of 1. And if you have a radius of 1, then simply, right, this is a formula that's used for finding the difference between 2 points. But in general, if I look at this circle, this distance is 1 unit. That's why they call it the unit circle, is because that length is 1. And if that length is 1, I mean, look at the point here. This is x, this is y. So clearly by Pythagoras theorem, x squared plus y squared equals r squared. And on the unit circle, x squared plus y squared equals 1 squared. X squared. Oh, this is deriving the equation of not just the unit circle. I'm sorry, but this is any circle. So I'm sorry, we're not supposed to have 1 there yet. This is going to be a radius of r. So in general, x squared plus y squared equals r squared, right? We carry on now and derive the equation of the origin with the radius of 2. Well, if the radius was 2 from that previous slide, then it'd be x squared plus y squared equals 4. And if it was 5 units, x squared plus y squared equals 25. But if it's 1 unit, then x squared plus y squared would equal 1. And don't forget y. I'm not trying to get you to memorize this. Look back. Clearly, x squared plus y squared equals r squared. Just simple Pythagoras theorem, right? So, when we look at a circle with a radius of 1 with the center at the origin, it's defined. That's why they call it the unit circle, because the spinner, the length of the hypotenuse everywhere around the circle is 1 unit. And because of that, it creates these special points of 1, 0, and 0, 1, and minus 1, 0. Those are special points around the circle with a radius of 1, right? But there's something else that happens. When r equals 1, remember that formula? Remember the formula that we've used in previous? Theta in radians is equal to arc length divided by radius. But in terms of arc length, you've always known that you can manipulate it, that arc length equals theta times the radius. But if the radius is 1, what this is saying is really r is irrelevant because it's just 1. So the central angle, I'm going to move this, the central angle is subtended by an arc of the circle have the same value. I don't know if you can see that. Have the same numerical value. All right? Given the coordinates of the unit circle, coordinates of the unit circle that satisfy. So if a point xy exists where the terminal arm intersects the circle, we can use Pythagoras' theorem all the way around. So in other words, if I've got x and y and there's a point on there that works, that's kind of helpful. We can do some work with it. So determine the coordinates for all points on the unit circle that satisfy the condition given. So in other words, well, what point would have an x value of 1/2 on the unit circle? Well, let's see. If it's got an x value of 1/2, that means it's over on the left. And so if I just simply use Pythagoras' theorem, well, that's pretty straightforward. 1/2 squared plus y squared equals 1. Ooh, this silly thing. So that means that 1/4 squared plus y squared equals 1. That means that y squared equals 3/4. That means y, whoa, I took the square root. So I need to include plus or minus. But why are there two answers? Well, there's two answers because having an x value of 1/2 means that it could be in two different places. It doesn't have to be up high. It could also be down low as well. And if it was down low, then it would be 1/2 and root 3 over 2, or 1/2 and minus root 3 over 2. So when you're asked about conditions like this, you have to consider all possibilities and be careful as you draw your diagram to kind of consider, wait, if the x value is 1/2, it doesn't just have to be up, it could also be down. And the math of it, taking square roots, you have to take both the positive and negative square roots, okay? The next condition says, hey, determine the coordinates for all points in the unit that satisfy this condition. Well, what about if the y value is minus 2/5? Oh, that's different. Again, we draw a diagram to see. Well, if y is minus 2/5, we now know it could be in two places. It could be in quadrant 4 or quadrant 3. I do Pythagoras' theorem, and once again, I come up with x could be plus or minus root 21 over 5. So the 2 points that exist are minus root 21 over 5 and positive root 21 over 5 in terms of places on the unit circle, right? What about the point minus root 3 over 2 and minus? Is the point of intersection, or is this point, what is the length of the radius, right? So we have the point on the unit circle. What is the actual length of the radius? Once again, we know the unit circle is defined by a radius of 1 unit, so if it's on the unit circle, the radius is 1. We didn't really need to do, but you could check it. You say, well, I'm not really sure. Well, we know that x squared plus y squared, and if you did check it, it does actually end up equaling 1, because you end up with 3/4 plus 1/4, but we didn't need to do the work because we know it's on the unit circle and the radius is 1. So as you read this next thing, it's basically saying, based on the arc length or the angle theta, I can ask for what point is at the end of that terminal arm, end of that arm of the unit circle. So if I said, what is the point at a certain angle of theta? So for example, if somebody said, yo, what's p at pi? What's the point at the end of the arm when you're at pi? Well, if you look over here, the point at the end of the arm when you went pi units around would be the point minus 1, 0. So point at pi is minus 1, 0. What about the point at 0? Well, clearly the point at 0 degrees or 0 radians is 1, 0. What about the point at 3 pi over 2? The point at 3, that shouldn't have a square root there, sorry folks. What is the point at 3 pi over 2? No square root, just 3 pi over 2. The point at 3 pi over 2 would obviously be this point right here, and that would be the point 0 minus 1. Okay, no square root, that's a typo. Okay. What about the point at pi over 6? Well, that's one we haven't done, but it'd sure be nice to know. But that's what we have to do now. So if the angle is pi over 6, what's this point right here? How much left is it? Sorry, how much to the right is it? And what's the x and y value? So I'd really like to know the x and y value for an angle of pi over 6, or 30 degrees. Your special triangles might be of help. That's what we need to figure out. So for Math 20-1, you built these special triangles. And I'm not going to review that here, but you do need to know that. So as we answer the question that was posed in that previous slide, we could take that angle of pi over 6, and that pi over 6 is related to this pi over 6, and this pi over 6, and this pi over 6 was quadrant 1, and this pi over 6. So in other words, that's actually the same angle as 5 pi over 6, and 7 pi over 6, and 11 pi over 6 as well. So that's related. Now, how do we know what those points are? That p function? Well, we simply need to look at our special triangles, as you're going to see right here. So if you look at your special triangle, all you need to do is take your special triangle, and like we talked last day, make this a unit. Make the radius 1. So convert to a radius of 1. So in other words, divide everything by 2. And if you divide everything, not the angle by 2, but divide all the sides by 2, and notice what happens. If you do that, now I'm going to do this in green, this length is 1. That's the unit circle. This length is root 3 over 2, and this length is a half. So what's the point, if you imagine putting this on the unit circle, what's the point at the end of this arm? Oh, well, this point right here is the point root 3 over 2, and it's a half in terms of the y value. A half tall and root 3 over 2 to the right. So what's that point in quadrant 1 where pi over 6 is the angle? It's root 3 over 2 and a half. And if you go over to quadrant 2, and now you're going to start filling in your unit circle. What's the point at the end of 7 pi over 6? Oh, minus root 3 and minus a half. All you're doing is reflecting these points around, right? So now we know all the trig values for all the angles related to pi over 6, or 30 degrees, okay? What about angles that involve 60? Once again, convert it to a radius of 1. And if you convert to a radius of 1, this would be 1, this would be a half, this would be root 3 over 2, which then makes this point, the point 1/2 and root 3 over 2 tall. So if you take this triangle and you superimpose it on your x and y axis, like we're going to do, what are the points at the end of all those related angles? Okay, well, I can erase this now and just allow you to do that, okay? So you convert it to radius of 1, and when you put it in all those quadrants, you end up with it reflecting around. And now you've got all the angles related to pi over 3, and 2 pi over 3, and 4 pi over 3, and 5 pi over 3. And again, I'd like it if you didn't just copy it. I want you to try and build it yourself. Or after you're done with this one, build the next one yourself, okay? So these are all the angles connected to pi over 3. What about the 45s? Exploring the patterns for, now, again, another typo. This is pi over 4. So exploring the patterns for pi over 4. Well, again, convert it to a radius of 1. This, you need to divide by root 2. So if you divide by root 2, this is 1, and this is 1 over root 2, and this is 1 over root 2. So when you do that, When you do that, you now take that triangle, and again, you're just going to superimpose it and put it in all the quadrants, pi over 4 and pi over 4 and pi over 4. And what are the points at the end of all those pi over 4 angles? Well, they end up being positive root 2 over 2. And you might say, well, Mr. K, how come those numbers are root 2 over 2? Well, they're just going back to Math 20. And 1 over root 2, if you multiply top and bottom by root 2, with a rational denominator is equal to root 2 over 2. Okay? And ask me tomorrow if that bothers you. But it's just rationalizing the denominator. Okay? So what are the exact values for each of those points? Root 2 over 2, root 2 over 2, 45 degrees. And in each of the quadrants, the points change to be positive or negative x values and y values depending on what quadrant they're in. Okay, so those are the exact values for 45. So when you go to summarize this, write down the points at the end of all these, right? And as you do it, can you build this all by yourself without looking here? Can you build the angles? Don't copy right now. Can you finish this slide off by yourself? Now notice that you really only need to do the first quadrant. If you can complete the first quadrant and get the exact values for 30 and 45 and so on, you don't need to do the others because all you're going to do is reflect them around the triangle to find the other ones. Okay? And once you do, you get this. That is the unit circle, you guys. We will use it tomorrow as we do our lesson. Take care.